So first of all, thank you for the invitation. I'm very pleased to be here, and I will tell you about my work in Stockholm University. I'm a PhD, and I study cooling dynamics of negative ions of C60 and C70 in the double electrostatic ion ring experiment in industry. Here I would say that I would disappoint Sebastian a little bit, because I'm not going to talk a lot more about Desiree, but mostly about the results that we have had so far. And anyway, I would like to start with motivation. And the motivation is that we know that fullerenes are in space, and we know this from the first observations in a young planetary nebula from the group of CAMI in 2010. They looked at the emission infrared spectra of C60 and C70, and also Gerard showed us the first very beautiful spectra the first day. And since then, a lot of other observations have come to place in reflection nebula, planetary nebula of the neutral species, but also in AGB stars and C60 plus, but also C60 minus in the Perseus molecular clouds. And there has also been laboratory confirmation of the bands of C60 plus. So under these facts, we just are faced with two very important questions in astrophysics that are about abundances and survival probabilities in space of these molecules. And what they do in astrophysics is that they have some astrophysical models, and what they input in these models is a lot of rates. And I'm just enlisting some of them here, like recombination, collision, ray ionization. And all of these rates of these processes, they depend on the internal energy of the molecule. So we're interested in the cooling dynamics. How does this internal energy changes as a function of time? So we are especially interested in the negative species of fullerenes, and the mechanisms upon which this molecule can cool down are firstly, and with a lot of high energy, it can dissociate. We cannot probe this with in our setup in Desiree, because we need higher energies and we create these fullerenes not so hot. But what we can probe is thermoionic emission, and when it's excess electron, just the negative fullerene decays into a neutral and the electron. And in a statistical description, we can write the rate of this process as a frequency factor times the rate, the ratio between level densities. And in one of these level densities, we have an important ingredient, which is the electron affinity of the molecule, of the neutral molecule. And despite the fact that it is very complicated experimentally to measure this in molecules, due to the high amount of thermally populated raw vibrational levels, I will show that in Desiree we can actually give a very precise measurement of this ingredient, of this physical property. Well, and here I'm plotting the rate of this process as a function of internal energy. In green is what we have with this function, and in black is the determined rate that was experimentally determined by Klaus Hansen. What we can also have is emission of photons. And we can have two processes. One is high energy photons, which Suvatika talked about, from this recurrent fluorescent process, which is basically the energy in vibrational modes interconverts into electronic excited state energy, and then it fluoresces with a very high energy photon. And we can see here the rate it crosses after 10 electron volts in this case in this system it crosses the green rate of thermionic emission, and then we will say that this process will dominate after lower than 10 electron volts. But we also have the low energy infrared photons that are given because of vibrational excited states. And if we look at the rate curve, we see that it's not, after a while, when the molecule cools down even more, then the process that is dominating is this, what we call ultra-slow process. So in this way, we can actually probe these two processes, and I will talk about this in the rest of my talk. So the thing I'm going to say about Desiree is it gets its outstanding capabilities from cryogenic operations, and the ultra high pressure, the pressure is about 10 to the minus 14 millibar, which translates to several hydrogen molecules per cube millimeter. The temperature is about 13 Kelvin, so we can actually simulate the conditions of outer space with Desiree. I'm just gonna use one of the rings, and what we do is that we create the hot fullerenes. We do bunches of these fullerenes, we guide them and we inject them into the ring, and we keep them stored for a certain while. And after this while, then we can dump them and we can measure how much was left from the ion bunches. And while they're inside, they will decay. And when they decay, when they're in each of these straight sections, the neutral products will fly just off to our detectors, the resistive anode here or an imaging detector here. And so what we can do is monitor the amount of this yield as a function of storage time. And here we have, I'm showing a neutral yield of the whole measurement as a function of time after creation. And note that this is log-log scale. And here what we can do is that we can fit a power law times an exponential. And if you look at the first, the very short times after creation, we see that it follows power law behavior, which is expected from highly broadened internal energy distributions of these molecules. And after a while, there is a quenching of this decay. And this is due to recurrent fluorescence. And the characteristic time of this process is around 12 milliseconds, which is in very good agreement with past works. And what we can do also next is that we can simulate this decay with this equation, the neutral rate, which is the internal energy distribution of it's the rate of electron emission and an exponential here. And the other rates, the rates of photon emission, are going to be the ones that influence this internal energy as a function of time. So we start our simulation with a type of Boltzmann distribution at 1300 Kelvin. And then from TDDFT calculations, we give an excited state. And actually this number is from also a measured experimental value. But the oscillator strength of this excited state is by TDDFT calculations. And we see that there's a very good agreement with our experimental data. We can do the same with C70. And we see at first that it is more, the characteristic time is 5 milliseconds, which means that it cools more efficiently than C60. So we can do the same simulation. And first, we have experimental value of one of the excited states, but by TDDFT, we found two more states. One is dipole forbidden. So we tried to simulate the experimental data with only one excited state, but we get this dashed line. And when we use both this state and the low-lying state, we get the solid line, which gives a very good agreement with our data. So this suggests that this low-lying state helps the C70 to cool down efficiently. So after a while, we reach the level of collisions with the residual background gas, so we cannot say anything more with this technique. So what we use then, it is laser photodetachment, threshold spectroscopy. And what we do is that we shine a laser in cross configuration, and in this case it's an OPO, 1 kilohertz, and we scan it across the threshold of the molecule. And when we do this, then what we measure is just the neutrals that comes from the interaction of the laser. And here I am showing the measurement, the counts as a function of storage time, and every photon energy it's color coded. And if we slice in time part of our data, then you see that we can reconstruct the relative photodetachment cross-section. And interestingly, if we integrate the rest of the data, then we see that there is this very sharp onset here that will correspond to the electron affinity. But before this, we see a bump, and it seems to be going away with time. So in fact, what we're looking at is the partial disappearance of excited vibrational states. And this is nice because in the past we were wondering about if these molecules will rethermalize in Desiree, and it turns out they don't. And the other thing that we were wishing for is that perhaps there is a better way of decomposing or isolating the cold component photodetachment spectrum from the hot component photodetachment spectrum. And we want to do this the best possible way without any sort of bias, analytical bias. So what we use is non-negative matrix factorization, which is an unsupervised machine learning algorithm. And it is a way of decomposing multivariate data from higher dimensions to lower dimensions. And it learns how to represent the data based on parts. And it does it with additive combination. And how it does it is that we have our data, and then it minimizes the distance between two positive matrices and the data, with the restriction that these matrices are positive. And it does the job, and I'm not going to show it yet. And if we consider the matrix W to be the weights of the matrix H, which are the components, and each of these weights tells how much of each component is represented in our data. And we are interested in two components, so we are creating, or we are telling the algorithm to find two components. And if each row is a time bin, and each column of this matrix is a photon energy. The drawback of this algorithm is that it doesn't take into account experimental uncertainties. So what we have to do is instead use a least squared NMF. And here, instead of minimizing this distance, you minimize the chi-squared value. But also, the error bars do not get propagated through this iterative process. And what we do instead is that we exploit the fact that this is a solution that has different local minimas. So what we do is that we initiate random matrices. We do it thousands of times, and each time it finds solutions that are different. And what we do in the end is we take the standard deviation of these different trajectories or solutions. And in the end, we can recreate the NMF. Oh, what happened? It just went crazy. Sorry. Spoilers. Yes, so it recreates the cold component of our data. So here I'm putting all our experimental data and the NMF component with LS-NMF, and here we clearly see that we can. So NMF is able to reconstruct a cold component in our spectrum, and then from here we can put the most precise measurements of electron affinity from different groups, and the LPTS most precise measurement is shown with this dashed line, and the measurement with photoelectron spectroscopy is here. So if we take a zoom, then we can fit our data with a Wegener-Law in convolution with the line width of the laser, and we can find that it's very good agreement with the best experimental value so far. So I'm not going to talk a lot more about this, but if you want, you can ask me later. Also about the LS-NMF. But what we can do now is that we can do the same for C60. It's a little bit more tricky, but then we also get a very good agreement with the photoelectron spectroscopy measurements. And now that we know where is the threshold of electron affinity, what we can do is that we can take all the things that are before, which corresponds to low vibrational hot bands, and we can integrate over time. And I'm going to do this with C70. We can integrate. Not working again. Okay. And we can put the integrated yield as a function of storage time. How do we simulate this? Well, I follow the development of two papers, Mark and James Bull, that they have used this this type of approach, and they consider that there is intermolecular vibrational redistribution, which is the flow of energy among all the degrees of freedom of the molecule, and based on this approach, we can solve a master equation for the internal energy distribution. And I'm not going to spend so much time on this, but you can see, if you solve this master equation, you can see how the internal energy distribution goes down as a function of storage time. If we take the mean of these distributions and we normalize it with our data, then we see that it follows until around 2-3 seconds, and then it just deviates a lot. This suggests that IVR is not efficient anymore after 3 seconds. So what we can do instead is that we can get another treatment. We can decouple the energy following the work of Christine Chauvelin, and we can negate the axis of this flow of energy. And what they do is that they take a cut of energy and they redistribute it among all the degrees of freedom in a random way, but with a probability distribution. And they construct decoupling rate. So we're following this, and just to put an example of how it is done, if we take a slice of the energy distribution, let's say 3 seconds, and we take a cut of energy, let's say 4,000 centimeter inverse, and we put, let's say that we randomly distribute it and all of our energy ends up in a short-lived state or a couple of short-lived states, then we individually track down this decays. And if we do it with this, then we get an energy that goes like this. If we do it again, then we can end up in a long-lived vibrational state. We do it like we can have this, but then we do it a lot of times. This Monte Carlo simulation, and we take the average, and then from the average we have this black solid line. But we have to remember that this distribution is shifting in time because the molecule is still cooling, and the thing that's important now is the cut-off energy here. And if we now think about, let's say, 4.6 seconds, we see that there's a lot more of distribution that is in this cut-off energy. So we can reconstruct, we can do a weighted average across all the storage time and each time we have to wait for this the amount of population in that cutoff energy, and we fit that, and we get something that it's more in agreement with what we see in the experiments. And this is C70. We can do it with C60, and both of them we realized that these decoupling energies are in the same order as they have measured before in other works. The decoupling energies are around 2000 centimeter inverse, and it has been measured in anthracene. So, to finalize, well, the conclusions are we can study cooling dynamics in these timescales from 100 microseconds to up to 100 seconds, and maybe a little bit more. It depends on the storage time of the molecule inside the ring. C70 cools more efficiently on shorter timescales. IVR is not efficient in longer timescales. So we can say that the energy gets frozen in long-lived vibrational modes. And we found the coupling energies that are in the same order of for anthracene. And also importantly, we have measured the electron affinity, and we find a good agreement with the photoelectron spectroscopy. And this experiment was done in cold conditions. And so this disagreement in the literature between photoelectron spectroscopy and LPTS, I think we have settled it down. And finally, I would like to make this work. I would like to acknowledge all my team in Stockholm University. There's a lot of names from current and former PhDs, postdocs, and also for the technical group that they're very experienced in what they do. And thank you very much for listening.
Very nice. Does anyone have any question? Yeah.
So very nice. Also very nice that this this photoelectron spectrum has been settled. Was that the one from Laisheng Wang, the correct one?
Yeah, the most precise is from them, I think. Yeah.
And I was a little bit amazed that you you said in the Boltzmann distribution that you started with 1300 Kelvin. Is that the temperature of the oven or so that you use at some point, or why? Because it seems so high to me.
Yeah, it's. I think I've read some works where they actually use the well, not 1300 but 1200, 1250. So it was sort of arbitrary, but it seems that several other groups have found the same type of conditions. So it was just like, okay, let's use this temperature because it seems like people have found these temperatures. Yeah.
Yeah. Any other questions? Yeah.
So very nice talk. I have a question about the IVR simulation. So correct me if I'm wrong, but to my understanding, usually IVR is inefficient unless it takes place in a redistribution into two different modes, or two. It doesn't necessarily spread across all the modes all at once. And so my question is, did you take this kind of thing into account? And the other question is so you're saying the IVR stops because you get down to a level where you have a low enough density, so that IVR is sort of prohibited, or is there?
Yeah, I think that maybe the two questions go together, and the thing is that this is, well, the first thing that I can say is that this was a statistical approach, and it is a sort of very huge approximation of just saying, okay, just switch it off at this moment in time, and basically that shouldn't happen in real life, because like if you go to a quantum mechanical description, then you will have to perhaps take into account that some of the modes are still flowing of they have flow of energy between each other, maybe. So there's three regimes. So this guy's from Felker and Sewell. They have studied three regimes of IVR. One in which IVR is not present. One in which they have these quantum bits, like these have oscillations, where it's kind of like an IVR with just several vibrational nodes that are playing with each other. And they have the regime where it's completely dissipative, like you have complete IVR. And their treatment is a little bit more complicated and more complete than in that sense. But as far as I know, and I think that this statistical treatment that should give a very good understanding about what is happening with the cooling dynamics at long time scales.
Okay, thank you.
Mm.
We still have time for a couple of more questions if you want. No? Yeah.
It was a very nice talk. I like this experiment, Desiree, especially from Silver Dimer. I would like to ask about non-negative matrix factorization. You used in this algorithm two components.
Yeah.
Yes. And why you do this? Only two components, and how many information do you lose if you use two components? And maybe it will be more efficient to use more components.
Yeah. I also try to use more components. So it's an ongoing thing that I'm doing. But the thing is that if we want to disentangle all the vibrational modes of C70, it has 204. So if you want to take more components, then why taking 3 or why taking 4? Why not 204? And it seems to me that you can have one component that takes into account all the vibrational signal, the hot band signal, and the other one the signal that it was able to identify as a signal that was cold in that sense. But yeah, I think that there's still some room for us to play around with this, but yeah, I will have to think about it.
It was problem with the interpretation of the other components.
Yeah, I think that interpretation is straightforward. You use two components than using more components.
Okay, thank you.
Mm.
Okay, let's thank the speaker again.